This is LoRA design, how to efficiently fine-tune large language models. We will go from the problem, to the architecture, to training, hyperparameters, and how you actually choose a checkpoint. The base model stays frozen. Only the LoRA parameters are trained. Full fine-tuning can update billions of parameters. Gradients and optimizer state explode memory. A separate fully fine-tuned copy for every task is also expensive to store and deploy. The question is, can we adapt the model without modifying all of its parameters? LoRA means low-rank adaptation. Keep the pre-trained weights frozen, and learn relatively small low-rank updates. The base model keeps its original parameters. Task-specific behavior lives in the adapter. You can keep one base and swap adapters. A pre-trained linear layer is y equals Wx. W is the pre-trained base model weight matrix, the big frozen layer in the language model. We do not rewrite W. LoRA writes an update as b times a, two much smaller matrices. The effective map is y equals Wx, plus a scale s times b. Axx goes through frozen W, and in parallel through a then b add the paths. Only a and b get gradients. Rank R is adaptation capacity, not a trophy. Rank 4 is small and cheap. Rank 16 is a common starting point. Rank 64 has more capacity and more memory. Lower rank can underadapt. Higher rank can fit dataset-specific noise. Higher rank does not automatically mean a better model. Check on scene data. Alpha scales how loud the LoRA path is. Many implementations use scaling about equal to alpha over R. But conventions vary. Treat alpha as a tunable hyperparameter, paired with rank, not a universal constant. LoRA dropout is regularization on the adapter path. Too little can help overfitting. Too much can stall learning. Values like 0, 0.05, and 0.1 are experimental examples, not rules. You also choose which layers get adapters. Common attention projections are Q, K, V, and O. You can add MLP projections, gate, up, and down. Names depend on the model. Adapting more modules increases capacity and compute. Validate the choice. W is the pre-trained base model weight matrix, the original frozen parameters of the language model. An example is tokenized. Then the forward pass uses W, y equals Wx, plus the LoRA path. Loss is computed. Gradients flow. And optimizer step updates only a and b. W does not get an optimizer update. One training example is not automatically one optimizer step. An optimizer step is one actual update to the trainable LoRA parameters. Forward, loss, backward, gradients, then optimizer step, then a and b change. Micro batches can pile up gradients before that step fires. Gradient accumulation lets you simulate a larger batch. Effective batch size is about batch per GPU, times accumulation steps, times number of GPUs. Example, batch 2, accumulate 8, 1 GPU, effective batch 16. Steps per epoch is about the number of training examples divided by effective batch. Total optimizer steps is about that times epochs. 10,000 examples, batch 16, is about 625 steps per epoch. 3 epochs is about 1,875 steps. This is an approximation. Packing and distributed sampling can change the count. Learning rate is how aggressively each step moves a and b. Too low, painfully slow, about right, stable descent, too high, the loss oscillates. LoRA learning rates can be higher than full fine-tune rates, but it still depends on the model and task. A reasonable search is 5 times 10 to the minus 5. 1e4, and 2e4, as experiments, not a law. Learning rate is how hard you push. Optimizer steps are how many times you push. High learning rate plus many steps can be unstable or overfit. Low learning rate plus few steps can underfit. Do not treat learning rate times steps as a precise total of learning. Adaptive optimizers, clipping, and schedules change each update. A typical schedule is warm-up, then peak learning rate, then decay, cosine or linear. Warm-up helps the first updates when gradients are noisy. Underfitting. Train and validation both stay poor. Causes include too few steps. Learning rate too low. Too little LoRA capacity. Weak data. Or a bad setup. Overfitting. Training keeps improving while validation gets worse. Then stop. Pick an earlier checkpoint. Improve data. Or reduce unnecessary capacity. Training loss alone is not proof the model is good. The last checkpoint is not automatically the best. Unseen data means examples the adapter did not train on, a held-out validation or test set. You score those to decide when to stop. Training loss on the training file can keep falling after performance on unseen data has already peaked. Keep the checkpoint where unseen metrics peak, not the step with the lowest training loss. Ask, at this learning rate, batch, rank, and dataset, at which checkpoint does unseen performance peak? A strong experimental baseline is Atom W, learning rate around 1E4, rank 16, alpha 16 to 32, dropout around 0.05, effective batch 16 to 32, 2 to 3 epochs, 3 to 5% warm-up, cosine or linear decay, gradient clip around 1, then actually try 5E5, 1E4, and 2E4. These are starting points, not universal optimums. Change one thing at a time. Baseline, then learning rate, then training duration, then rank, then target modules, then regularization, then the dataset, then a final evaluation on untouched test data. If you twist every knob at once, you will not know why the score moved. 5 decisions: data, capacity, learning rate, optimizer steps, and validation. Unseen data means held out examples never used in training. That score decides when to stop, not training loss on the training file. The goal of LoRA training is not the lowest possible training loss. The goal is to learn the desired adaptation while keeping strong performance on unseen data.